Hey everybody, welcome back. It's Ripley. I'm going to show you another really cool application of the definite integral. It's actually kind of fun, and it's incredibly simple, and as always, incredibly elegant in terms of how they came up with it. So check this out. Say that by the time we're done, we're going to, with this section, hopefully you'll be able to figure out how to find an arc length of a curve. So watch how cool this is. So let's say that I have a function f of x. And I'm trying to figure out not the area underneath the curve, but let's say that I'm trying to figure out how long the curve is from between two fixed points. So on a closed interval, right? So how long is that curve? Now watch how simple this is. So cool. Pick any 2 points, right? I got x1, I got y1, right? And then up here I got x2 and I have y2. If I want to figure out the arc length, do you agree that I could use the length, I'll go with orange, I could use the length of this line segment as an approximation, excuse me, right? Now, think about this from an integral standpoint. If I take that line segment and I call that my action, right? And then I let the number of those line segments go to infinity, and therefore their lengths would shrink to 0. Wouldn't that do it? Because what I'd end up with is just a bunch of points. Whoops. And the integral allows us to add up those bunches of points, right? You agree with that? So watch how this works. It's really cool. Do you agree that this distance we could refer to as delta x, and this distance we could refer to as delta y, right? So the length of my ith interval, and that would just be the interval between x1, y1, and x2, y2, is just simple distance formula. It's delta x squared plus delta y squared, right? You agree with that? Nothing to it. Now, I'm going to do something funky, but I've done it before. I'm actually going to multiply by the square root of, let's go, just for fun, let's go delta x squared over delta x squared, which is just a goofy looking 1, so I've changed nothing. Now watch what happens here. This tells me that the length of this ith interval, this ith segment really is what it is the square root of delta x squared divided by delta x squared plus delta y squared divided by delta x squared, and then outside I have a delta x, don't I? Now watch what happens. Whoop, that goes away, and I end up with the square root of 1 plus delta y over delta x squared times delta x. Now all that is the length of this ith line segment. If I want the length of the entire segment, can you think about how to do that? Well, I'm going to add up an infinite number of infinitely thin segments now. Instead of rectangles, we're just talking about segments. And how do we do that? Oh, we have this wonderful tool called the integral. Now, when we go from the length of the ith to the length of the overall curve, we use this little script out because it makes us look smart and it looks pretty. All right, and this is simply the integral from a to b of the square root of, now 1 is 1, right, plus, well, what happens as I let delta x and delta y shrink to nothing, because that's really what's happening, right? This guy's shrinking back to here. As that happens, delta y shrinks to an infinitesimally small quantity, and these turn into dy over dx's, right? That's literally what Leibniz meant when he talked about these differentials, squared times, whoops, dx. That's the length of an arc if you have a function of x. Now, what do you think happens if instead of a function of x, I'll just do a quick little sketch, I won't bore you too much. What do you think happens if this is an f of y, right? And I'm going from a to b. Well, let me just show you how we change what we do over here. Instead of multiplying by this goofy looking 1, we're going to multiply by this goofy looking 1. Which is delta y squared divided by delta y squared. Some of you may be going, wait a second, Ripley, what's going on here? You always told me that the square root of something squared is the absolute value, so shouldn't this be absolute delta x? Well, yeah, except we're saying that delta x is a distance, so we know that it's always going to be positive. Now, watch what happens here. I know that this implies that the ith interval is going to equal the square root of delta x squared divided by delta y squared plus 1. So the overall arc length is going to be the integral from a to b, times, of course, delta y. So the overall arc length is going to be the integral from a to b of the square root of dx over dy squared plus 1 dy. Now that's if you have a function of y. Now I know your spidey sense is tingling. I know all of you naysayers out there, well, what about parametrics? What the heck happens if I have a parametric? So now, this is especially poignant because I could have a curve just going, yeah, woo! And let's say that I start this at t equals a, and I finish it down here at t equals b, and I'm trying to figure out how long this length is. Well, guess what? Same trick. L sub I is going to be equal to the square root of, now, can you see what's going to happen? I didn't leave myself enough room, but I'm going to multiply by a different goofy looking one. And I'm going to end up with the square root of delta t squared. This is my goofy looking one over delta t squared. So in here I end up with delta x squared divided by delta t squared plus delta y squared divided by delta t squared times delta t, you guessed it. The overall arc length is going to be the integral from a to b of the square root of dx over dt squared plus dy over dt squared times dt. So cool. Now, the only thing that you really got to pay attention to is these limits, because this can get funky, because you notice that this f of x, I wrote this as y equals f of x. I could just as easily write this as x equals f of y, and I could get really tricky when I do that, so be careful what your limits are. In this case, we got limits on x. Remember, this guy right here always tells you what your limits have to be on. In this case, we got limits on y. Again, dy tells me, hey, look on your y-axis. This is a little trickier, right? Because we don't necessarily have a function that we can talk about, but this just says your limits have to be on t. Limits on t. Now, I don't mean to be glib when I show you this formula. The formula is really cool and it's really easy to make. That doesn't mean that the integrals necessarily are going to be really cool or really easy to do. They can get pretty tricky. So what we're going to do tomorrow in class is we're just going to do a whole bunch of integrals. I'll throw them at you. And the trick is don't panic so much when you see the integral. And just remember, oh, I'm just taking an integral. I'm going to reach into my integral toolbox. Excuse me. I'm going to reach into my integral toolbox and take an integral. All right? Thanks for paying attention. Have a great day, and I'll see you tomorrow. Bye-bye.